Welcome to Exam List, and in this lecture series, we'll talk about wave packet concept and the minimum packet idea. Okay, so the question is why there was an introduction of the idea of wave packet in quantum mechanics. Okay, so the idea of wave packet is nothing new. It has its origin in the wave mechanics that you've already studied in your classical physics. For example, um, if you have two waves, okay, so consider this is wave number one and this wave is of this form. Okay, so say this is a wave on a rope or a wave on a string, etc. And now consider another wave, okay, which is say fast varying. Okay, so its wavelength is small and frequency is high. Then what happens when you add this type of two waves? So if you try to generate these two types of wave on a single string, then you will end up with a string that will look like this. Okay, so you see an interesting thing about the resultant wave. So what do you get? The resultant wave that you get is a wave packet. So these are called as a wave packet because there is no constant amplitude here. Okay, there is no constant amplitude here, and the wave packet travel with a velocity called as the group velocity, so its velocity is different. These waves has a unique k, they have a unique lambda, they have a unique frequency, hence they have a unique velocity. These type of velocities are called phase velocities because we know that if we know lambda and frequency, then we can easily calculate the velocity of a wave. So velocity of this wave is lambda into f. So this wave has say different lambda and a different frequency, then phase velocity will be different because the phase velocity of this wave will be lambda dash f dash. But when you combine these two waves, then the resultant is a wave packet. Okay, and this wave packet moves at a velocity different from the phase velocities of the first one and the second one. So it is quite different from the phase velocities. Now question is, can we mathematically define this type of wave packet? So this is a diagram. How can we look at mathematically? Yes, this is true. So let us do the calculations. Okay, so mathematically what you need to do, you need to take two waves. So say this is wave number one, okay, and wave number two. The two waves must be different in their lambda and different in their frequency. So if I say two waves has different frequency, then indirectly they have different omega. Now if I say the two waves has different wavelength, it means indirectly they have different k, because omega is related to frequency by the relation omega is 2 pi into frequency, and k is related to wavelength by the relation 2 pi by k. Agreed? Okay, so let us now take two waves with different omega and different k. So consider wave number one is y is equals to, see, let me remind you, we are doing just the classical wave mechanics. Okay, we are not doing anything new, nothing quantum here. We are just doing the classical wave mechanics. So wave number one is a cos omega t minus kx, and wave number two must have different omega and different k. So the plan is just change these omegas by a few value. So the second wave, say this is y1 and this is y2. So second wave will be cos. Okay, so what is the trick? Don't write a different omega. So make the omega a bit increase, just increase the omega. So write omega plus some value of del omega. Okay, so when you add an extra omega, it indirectly indicates that the omega has changed. So omega t minus, and just little bit change in k. So how to change k? Just add some extra k. Okay, so it shows that the new wave has a different k. So omega plus del omega t and k plus del k x. Agreed? Now what to do? Now you just add them. So y equals to y1 plus y2. Agreed? Now try to understand something here. You did addition of waves. Okay, so for example, if you have similar waves coming from this side and this side, so if you have similar waves coming from this side and this side, then what you did, this wave you write y is equals to a cos, okay, omega t minus kx. Okay, and the second one that is going towards the opposite direction was written as the same uh, the same one, but there will be an extra plus sign. Okay, but there will be an extra plus sign. So when you added them, remember you got standing waves. So what was the formula? The final one you got was 2a. So you had something like cos omega t and sine kx, something like that. I don't particularly remember now. Okay, so something like this. So the space part and the time part were different. So take a look, just add them and just take a look. So here what I want to say is, here you won't get standing waves. Okay, because this is two waves y1 and y2, both are in the same direction, so both are going from left to right, and then you have added them. Interesting thing is both have different lambda and frequency. Agreed? Okay, so let us add them and let's see what do we get. So the first thing that we need to add is this part, and the second thing that we'll add is this part. So let me write it down. Okay, so how to add them? So consider this entire omega t minus kx as a, and this entire part here as b. So this is like cos a plus cos b. Agreed? So you know the formula. You can just apply the formula as 2 cos a plus b by 2 and cos a minus b by 2. So what is the answer? So there will be a 2a. Okay, so this a is not to be confused with the a inside, so 2a. So cos a plus b by 2. Okay, so there will be cos. So what is a plus b by 2? So you have to add omega t minus kx with all these things. So you will be left with, so let us do it in the new. Okay, so I have written it down. So you can see, you can just simply do this algebra from here to here. It's very easy. All you have to do is 2a will be outside. So this one is cos a plus b by 2. So this a, so omega t minus kx, this will be a, and the second part will be b. So just do a plus b by 2 and this will be a minus b by 2. So this is the result. So simple algebra. Then this is also used. So cos of minus theta is cos of theta. This part is also used in the second term. So while you solve it, you can easily get it. Now what we can do is, we can assume this delta omega so small that we can write 2 omega plus delta omega approximately equals to 2 omega. Okay, because we have assumed the delta omega is very small. Similarly, you can write 2k plus del k. Okay, assume this delta k is also very small, so this can be also approximately written as 2k. This is done just to simplify the equation. So what is the answer? Okay, this is the final answer. So this equation is different from standing wave. Okay, this is way different from standing wave, and when you plot this, you will actually get something called as beats. Okay, so the beat phenomenon is a common phenomenon when you add two waves with different frequency. So how the beat will look, as I've already drawn earlier. So if you have a rope and if you add two different waves, then this is how a beat will look. So there will be sudden increase in amplitude and there is a decrease in amplitude. Okay, this is the concept of beat. This is also called as a wave packet, because you see the reason it's called as wave packet, because you see this is one packet. Okay, this is another packet. So the wave is moving in the form of packets. Okay, so the wave is moving in the form of packets. Now, as I said, so this equation represents this wave packet. Agreed? Now question is, with what velocity is the wave packet moving? Because see, whenever you are given a wave equation, so consider this wave equation y1. So whenever you are given a wave equation, you can calculate the velocity. So the velocity for the y1 will be omega by k. Okay. So this is the velocity. But here, this equation of the beat is very much different from the general wave equation. So you just cannot multiply some omega with some, just cannot divide some omega with some k and get the velocity. No, you can't do that. So now the question is, with what velocity is this moving? Okay. So the answer is that it moves with a velocity called as a group velocity. And this group velocity is equals to d omega by d k. Okay. This is the velocity with which the wave packet is moving. Now question is how to visualize this. Okay. So let us try to imagine this wave packet, and let us try to visualize how with this wave packet is moving and with what velocity this wave packet is moving. Okay, so we have written it here and we have emptied the board. So now question is how to imagine. Agreed? So what you do is take t equals to 0. So let us visualize the entire wave, or how the wave looks at t equals to 0. So what will be the value of y at t equals to 0? Let me write it down. Value of y will be, okay, so this is the wave function at t, this is the wave at t equals to 0. I should not say wave function. So it is the wave at t equals to 0. So let us plot. Okay, so let us plot. So consider this part. So consider this part as a dash. Agreed? And let us plot a dash with respect to the space. So as you can see, so this is a dash is the amplitude and x is the space part. Now as you can see in a dash, that del k means the small k. A small k means large lambda, because k is related to lambda in this manner. So 2 pi by lambda. So if you are taking a very small k, it means the lambda is large when the k is small. It means if I can plot a dash with respect to x, then obviously the lambda will be bigger. Agreed? Now the question is, what are the values? What are the values? So the values are as follows. So this point, as you can see, will be 0. Okay, and oh, since this is a cos wave, so I mistakenly drawn the sign. So since this is a cos wave, so the diagram will be from here. Okay, this is the diagram. So this is a dash. So what is the value of a dash at various points? Let us see. At 0, the value of this is 0. At this part, the value is pi by delta k. Okay. Now at this part, the value is 3 pi by delta k. Okay. So this is your task to figure it out how I can write this. Is very easy. So if you have good understanding of wave, you can do it. If not, you can go through our wave and oscillation CD to get a clear understanding. So we have plotted a dash with respect to x. Okay, so the first part is done. But you see, things are not complete because we have the second part that needs to be understood. It is a combination of first part and the second part. So now what I'll do is, if I draw the second part with respect to x, then you see the value of k with respect to the first one is larger. It means large k means small omega, large k means small wavelength. So and this is the diagram. So as you can see, it's also a fast varying wave because the wavelength is small, so it's very fast varying. Now when you combine these two, because the wave is a the answer y, or the final wave y, is a combination of first part and the second part. So it's a combination of these two diagrams. Okay, so when you combine these two diagrams, what will happen is that you'll get this. So the slow varying part will form the upper part. Okay, so the green one, they will form the cover. So it will look like this. And the red one, the fast varying part, will be somewhere inside the cover. So they will look like this. So when you combine them, this is what you will get. So this is the idea of wave packet that I was discussing earlier. Okay, this is how the wave packet is gonna look. So these are all waves, agreed? So this red one is a real wave whose amplitude is varying with respect to space, as you can see. So this is the idea of a wave packet. So you can see um, it is not exactly a wave packet. Okay, so these are actually called as beats. So though I was saying, but the actual word that will describe this is beat. When I say wave packet, I would only mean, so in future if I say wave packet, then I would only mean only this. I would mean only this. That is a beat confined to a particular region in space. So a beat confined to a particular region in space can be treated as a wave packet. But this is not confined in a region because this is, as you can see, it extends from 0 and it goes all the way along the x. Agreed? So this is the idea of beat, and in quantum mechanics we will be interested in this idea. We will use this idea and we will reach to the concept of the wave packet. Agreed? So the next question we need to answer is that with what velocity is this beat moving? With what velocity is this beat moving? You see, the velocity is defined by the green part. So this green part decides the velocity. So what is the velocity? The velocity is decided by the green part. So in the green part we can see the omega part contains del omega by 2 and the k part contains del k divided by 2. So what is the velocity of the beat? It is del omega divided by del k. So this is the group velocity. So why it is called group velocity? Because the velocity of the beat is decided by the green part. The green part is the slow part. Agreed? The green part is the slow varying part and the red part is a fast varying part. By fast I mean the frequency is large and the green part the frequency is less. So the green part forms the upper cover and it decides the velocity of the beat, and the velocity with which the beat travels is called as a group velocity. Now we will, this is just all classical. Agreed? This is just completely classical. Now question is how to incorporate this classical beat phenomenon into quantum mechanics, and second question is why do we need to incorporate this idea into quantum mechanics. Okay, these two questions we'll discuss in the next lecture.